Okay, so before we learn the ideal gas law, we should go over all the other laws. So Boyle's law states that pressure, oh, that's a V, well, it's included. Pressure, just change it, times volume equals a constant. This is a K. And Charles's law states that volume over temperature equals a constant. Gay-Lussac's law states that pressure over temperature equals a constant. Avogadro's law states that volume over the amount of moles present, which is represented by an N, strangely enough, equals a constant. And the ideal gas law, which is pressure times volume over the amount of moles present, N again, times temperature. And temperature is always represented in Kelvin, no matter what. So if it's given to you in Celsius, you have to change it to Kelvin, which is by adding 273 degrees, or just 273. And this also equals a constant. So then that's the ideal gas law. And then when we factor in R, which is the ideal gas constant, that finishes the ideal gas law. And R, its units are dependent on the units of the pressure in your problem. So if your pressure is an ATM, your R will equal 0.0821 liters times ATM over moles times Kelvin, because T is always in Kelvin. And if your pressure has units of millimeters of mercury, it equals 62.4 liters times millimeters of mercury over moles times Kelvin. And then, if your pressure units are in kPa, it will equal 8.314 liters times kPa, that's an ugly P, over moles times Kelvin. Okay? So once we factor in the ideal gas constant, which is R, we get PV equals nRT. Okay? So that's the first part. Draw a little box. Okay. So now to the practice problems. So page 473, number 42, are the practice problems in the book. Okay, so it states that you have your pressure is equal to 143 kPa. Your volume is equal to 1 liter. The amount of moles present is equal to 2.49 moles, obviously. And R, your ideal gas constant, since the kPa, we go back down to here, and your ideal gas constant will equal 8.314. So we put that, 8.314, and then you could do liters times kPa over moles times Kelvin. Okay, it's asking for temperature, so we don't know what temperature is. And it always has to be in Kelvin, so remember that. But it's asking for our temperature in Celsius this time. So when we solve it out, we'll have to subtract 273 to get to Celsius. Okay. So we plug it in. Since we're solving for T, the equation is T equals PV over nRT. So T equals 143 times 1 over, where's N? Oh, 2.49 times R, which is 8.314. Oh, we don't need a T right there because we just solved for that. We're trying to solve for that. Okay, so that's what it is. And when you solve that out, you get T is equal to 6.907591878. And since that's obviously way too long, we're going to round that down to 690 minus 273 equals, and it's equal to negative 266 degrees Celsius, because we have to subtract that to get to the Celsius, because this is what it is in Kelvin, and this is what it is in Celsius. And this is your answer. Alright, so now, also on page 243, number 43, ask you to solve for volume. So your pressure is equal to 0.900 atm. Your volume is equal to, we don't know because we're going to solve for that. The amount of moles present is equal to 0.323 moles. R is equal to 0.0821 liters times atm. Oops, forgot to write that. Over moles times K. And we got this from right here because the pressure is an atm, so the ideal gas constant will be an atm. And our temperature is nicely already given to Kelvin in us, and it's 265 Kelvin. Okay, so since we're solving for volume, the equation is V equals nRT over P. And, so we plug in our numbers. We'll go right here. V equals 0.323, that's the amount of moles, times 0.0821, which is the R, our ideal gas constant, times temperature, which is 265, over pressure, which was 0.900, and when we solve that out, we get V equals, 7.80816611. And when we round that to sig figs, V equals 7.81 liters. So that is your answer for number 43, and that's how you solve for volume. And every time for whatever it asks for, you have to manipulate the equation to get the thing that you're solving for all by itself. So up here we got T all by itself, and up here we got V all by it, or down here we got V all by itself. And yeah, and make sure T is always in Kelvin, and make sure your ideal gas constant matches the units of your pressure. And that's how you solve ideal gas problems.